start. Okay, so let me give you a brief introduction. So thank you everyone coming to our today's seminar. A quick intro in case this is your first time joining our seminar. As you may know, CHAI Hub is a multi-institution research hub focused on developing AI technology for healthcare that uses causality to make better AI systems. This is our monthly seminar where we invite speakers to exchange knowledge and discuss recent developments in AI and healthcare research. Today we will be hearing from Dr. Sander Beckers, who is a postdoctoral researcher at University College London. Sander is a researcher whose work bridges computer science, statistics, causality, AI ethics, and the philosophy of science. He earned his PhD from KU Leuven and has held research appointments at several leading international institutions. Currently based at UCL, he focuses on causal modeling in AI and healthcare. His research explores how causal explanation, counterfactual reasoning, and model abstraction can advance the development of trustworthy and interpretable AI systems. Within the UCL's CHAI Hub, Sander contributes to projects that apply causal reasoning to advance healthcare AI, making sure such models are not only predictive, but also explainable, responsible, and ethically sound. Does that sound good, Sander?
That sounds yes, excellent. Like I didn't even realize there's so much going on. Thanks a lot for the introduction, and I'm happy to pitch in kind of last minute and give a talk for our CHAI community. Now, I have the fortunate excuse that I can use that it was a bit last minute, and therefore this is not the most polished talk that I've ever gave. Also, the topic I'm going to be talking about, it's something that hasn't been on the forefront of my mind for a few months. So it's a way, a reacquainting myself with it as well, just as you'll be acquainted with it. And I'll be talking about something I think is crucial, and everybody kind of realizes it is crucial, but it's, I don't think sufficiently understood how problematic it is and how the formal tools we currently have at hand are not yet capable of addressing the challenge. The challenge being ambiguous interventions. And the other part is causal abstractions, because the most natural response when someone says interventions can be ambiguous might be, well, we could use causal abstractions to deal with this. That's indeed one of the motivations that people have had for causal abstractions. And I'm going to argue that that's not quite true yet. As causal abstractions are currently understood, they're not really capable of dealing with this. So the talk is mostly going to be setting a problem and not offering that much in the way of a solution, but more like a research program or things that we should be focusing on. So there are a lot of sections, but I won't, just in case somebody had some questions for Q&A, that I have some extra slides, but I'm not going to go through all of this. I'll start with just setting the stage in terms of the high-level description of the problem I'm tackling. And since abstractions will play a crucial role, I'll have to give you some background on abstractions, but I'm hoping that most of you are already familiar with it, because it'll be too quick for anyone who's never heard of it to be able to understand everything I say. Then I'll have to make clear what exactly I'm talking about with ambiguous interventions. So let's have to disambiguate ambiguity. And I'll say that there's three situations which look like they could correspond to ambiguous interventions: stochasticity, marginalization, and abstraction. And I'll say only one of these three is really the problematic case which properly deserves the term ambiguous intervention. And that's the one that hasn't really been dealt with. So I'll suggest, or I'll mention 4 possible solutions. The fourth is simply a call for a more general approach to abstractions that handles this, and I don't yet have such an approach, so that's why there's no section for the fourth solution. The first solution is something that existing literature that tries to tackle the problem already in a limited setting, and then I'll go through the other 2 solutions in a bit more depth, because those are going to be the main topic, I'd say, of well, partly negative and partly positive a view on ambiguous interventions and what we can do to handle them. So here's a couple of examples. Imagine that we have a variable for total cholesterol, and we have some way of changing that. We have an intervention that we can do, for example, giving a particular kind of medication, which changes the total cholesterol. And researchers do this, and they find that somehow changes in cholesterol have different effects for different populations, or even for the same population, sorry, for different members of the same population, and they can't really get a handle on why that is. So the effect being the risk for cardiovascular disease. Sometimes it's a positive effect, sometimes it's a negative effect. At some point, they realize, you know what, total cholesterol is actually the sum of two different kinds of cholesterol, or cholesterol is not a proper scientific term, but let's just go with that for simplicity. There's something called LDL, there's something called HDL. Total cholesterol is the sum of both of these. And the one is positive for heart disease, the other is negative, a negative contributor. So if your intervention is simply saying, I'm going to change the level of cholesterol, but you don't know whether it's something that is changing LDL or HDL, there's ambiguity. And the effect is not going to be identified precisely because of this. A more trivial example is, let's say that the variable we have is whether or not you're being assigned surgery. That's the high-level variable. It's just binary. But it may be that in a particular hospital, the surgery can then be performed by the surgeon who works on Monday or on Tuesday or on Wednesday, and each of these surgeons are slightly different. And therefore, the effect that will happen for each of these is going to be a bit different. So the variable surgery is ambiguous in this regard. A more realistic and interesting example is exercise. There was a recent study which showed that for people who had had cancer, the risk of recurrence of cancer was reduced by doing a particular type of exercise, which is calculated in terms of MET hours. And so the variable here is MET hours, metabolic equivalent of task, and that abstracts away entirely from whatever form the exercise takes. All that matters is that a certain amount of calories are consumed for a particular hour during this exercise. Whether you go running, whether you go cycling, supposedly it shouldn't matter. But of course, you could imagine that if you were to dive into the details, different forms of exercise that both achieve the same level of MET hours would have different effects. Lastly, obesity. Obviously, obesity is linked to many healthcare issues. And if you want to intervene on that, well, it's not at all clear what that means. There's many different ways of changing obesity, and they're not all going to have the same effect. So if the intervention is simply captured at the level of change obesity, then it's ambiguous. Now, these examples that I just gave, they're not chosen by accident. They all come from papers. So the first is the classical example by the philosophers Perthes and Shines, who introduced this notion of ambiguous intervention in the philosophical literature, making clear basically that the causal inference methods that existed, including the ones that they developed, are all assuming there is no ambiguity. And the moment there is ambiguity, we have no guarantees whatsoever that we're going to do anything sensible. So they set out the challenge of dealing with this, and I don't think the challenge has really been met so far. The second example is from a standard textbook on potential outcomes. And as I said, the third example about exercise is from a very recent study, actually, for the first time, an RCT on doing exercise for people who had cancer, and it was very mediatized, to got a lot of attention. And the last one is a famous case from a paper by Hernan on trying to explain the potential outcomes, that a treatment variable should always be made as clear as possible so that anyone who's applying the treatment knows what protocol to follow. But at the end, he also says, there's only so much you can do to clarify. And at the end of the day, you just have to hope or assume that the level of clarification you've given is good enough to remove any ambiguity. But you can't test it, so it's basically a hope. Okay, so this is, I hope, clarifying already to you that what the problem is at hand here. And if you're familiar with abstractions, you might think, well, that's great. We can just represent all of this with causal abstractions. What we're going to do is we're going to take the ambiguous variable, and it's a high-level variable. It's abstract. And the effect that we're interested in, the outcome, is also going to be a variable in our high-level model, MH, right? H stands for high level, and M is the causal model. And then the fact that there are specific versions of each value at the high level is going to be captured by the fact that there's a low-level causal model. And the specific effects also live in the low-level model. And so we have a causal model ML. And these two models are both describing the same domain, but simply with using different variables. And the idea would be, if you represent it formally like this, then we could somehow figure out how the ambiguity at the high level still allows us to infer things about the effect in the high level. And also to allow us to quantify what the loss of accuracy is if we have ambiguity. For example, you could use approximate causal abstraction, which is intended precisely to say, what if the high level and the low level model aren't perfectly in line with each other? How could you quantify the mismatch? Or other frameworks that do try to achieve something similar. Now, this picture would be nice if it's correct, but I'm claiming it's not correct. It's not gonna work. So these are 4 claims that I hope, if you at least believe that these are plausible by the end of my talk, then I've achieved my main purpose. So the first one, that understanding ambiguous intervention is crucial. I hope for anyone in causal inference that's kind of taken as a given. The second claim is that abstractions aren't general enough currently to properly deal with this. The third claim is that an approach that I've developed recently by generalizing causal models to be non-deterministic offers one alternative notion to capture ambiguous interventions that we might explore, but take that with a grain of salt, because I certainly don't think it's the best notion in all circumstances. So therefore, the fourth claim is that we should look for a full generalization of abstractions that allows to deal with ambiguity in general, not only in some specific set of cases. And I'm not going to give you such a framework. That's more like a call to arms for all of you to develop one. So first, I'll have to say something about abstractions. I'm going to base myself on my own work because I'm, as you might imagine, most familiar with it. And there are different variations of the same idea that are being spelled out. So mostly it's just a matter of preference how you want to spell it out. The idea is that we have a causal model consisting of endogenous variables and exogenous variables. We have structural equations. So this is a structural causal model where the endogenous variables are deterministically determined by their parents. And in addition to a causal model that is required for abstractions is we have a set of allowed interventions, because not all interventions will be sensible or will be meaningful, and therefore you make explicit what the interventions are you're going to allow. And then as a standard, you could add probability to this by adding probabilities over the exogenous variables. And this will then induce probabilities over the endogenous variables in a standard manner. And it's, I think, clearer to work at the level of the deterministic model to clarify all the definitions, and only afterwards consider what would it look like if the entire model is not given as a structural causal model, but only probabilistically. Okay, so what is the idea? We have a low-level causal model ML, which is with its respective variables and equations, all indicated by subscript L. And similarly for MH, and assume that we have a function telling us how the endogenous variables, or the values at least of them, are being mapped to values of the high-level variables. That is our function tau. It's our abstraction function. And assume that we already know what this is, and therefore gives us a way of translating statements from the low level to the high level. Now we would like to somehow generalize this translation to the entire causal model so that we can translate causal queries from the low level to the high level and see whether they're still in line with each other. In other words, whether or not the high level MH is indeed a faithful abstraction of the low level, so that if we apply tau to the low level causal model, we get MH. And so we need to make clear what it means to apply this function tau to the whole model as opposed to simply these low level variables. Now, the way to get there is that you can consider a causal model itself as a function. You give it a context, which is a set of exogenous variables, the values of those. You give it an intervention, and it tells you what the values are for the endogenous variables. That's all a causal model encodes. So we already have a tau which maps VL to VH, again, values of those variables. So we just need to find functions for the other two components, for the exogenous variables and for the interventions. And if we have those, then we can make precise what it means that the high level indeed is a causal abstraction of the low level, namely that for any particular choice of low-level exogenous variables, so little ul, so the little u standing for the values as opposed to the variables. So any choice of ul, any choice of low-level intervention, there's 2 ways of computing the high-level effect. The one is you stay at the low level first, you compute the low-level outcome, and then you use tau to go up to the high level. Another way is you immediately go up to the high level by using these 2 additional functions, so that the low-level context goes to the high-level context, the low-level intervention goes to high-level intervention, and then at the high level, you compute the effect. And if both of these ways of computing it always agree, then you have a perfect abstraction. If it's not perfect, then you can try to approximate it somehow by looking at the distance between the 2 outcomes that you could have, depending on whether you have a distribution over all possible context intervention. You can look at the expected case. You could also look for the worst case, because perhaps for interventions you don't have a distribution. There's different ways of playing around with this, but then you can somehow quantify how well the two approximate each other. Okay, now I just should specify a little bit. I'm not going to say too much here, but the crucial point is that the function for the interventions, omega, it can be inferred from the behavior of tau. So essentially what it says is, take a low-level intervention. For example, y is being set to little y. If it is the case that all you need to know about the input to tau is that y equals y, then it's determined already that at the high level, z equals z, and it's also completely undetermined what the other variables will take at the high level. If that is somehow the case for tau, then you can use omega as simply representing that fact. If that is not the case, then omega is not defined on that intervention. That's a rough idea. So you want to somehow exploit the behavior of tau, that sometimes it can take partial arguments. And in those cases, you can use those partial arguments as defining your omega, and otherwise you're just staying away from the intervention. Okay, this is the background on abstractions. Why did we need this? Because it allows us to clarify what ambiguous interventions are. So informally, and I guess that's the most important statement to grasp, there's ambiguity if we have two versions of the same treatment. In other words, a variable taking on the same value, and they sometimes result in different effects, even under identical conditions and for the same unit or individual. Right? Because of course, in general, it's not at all surprising that the same treatment results in different effects because there's lots of different covariates. The point here is that even if everything else is held fixed, there still is going to be a difference in outcome. And abstractions allow you to make that precise by saying, if there exists two low-level interventions, for example, W1, W2, and they're both being mapped to the same high-level intervention, C, and there exists some context in which computing the effect for these different interventions would give you a different outcome. Then there's ambiguity. Okay, now that's a very general framing. How could this show up? There's three situations that look like they could be representing ambiguity. It could be because you've marginalized some variables. So take a very simple example. At the low level, we have a variable y, which is determined by two parents, x and z. And we've just simply marginalized z. That's all we've done, and that's our high level. Y equals some function of x, right? So we don't represent some crucial detail that existed at the low level at all at the high level. The second case is that the low level detail is represented, but it's represented ambiguously. For example, coarse graining. So imagine that we simply have y as a function of some low level x, and low level x takes values between 1 and 100, and we're going to now introduce a abstract variable xh, which is binary, representing, for example, that the value 0 could represent the low-level variable being 1 to 40, and the value 1 could represent 41 to 100, something like that. And then you would move from a deterministic model at the low level to a probabilistic model at the high level. The last situation could be that it's simply the case that the effect is partly truly stochastic. Even if you have all the identical conditions, there's just something out there that makes it vary. Now, this is standardly represented by just adding some new pseudo variable epsilon, and that's a noise term. And you just need to spell out then a distribution over epsilon, and you can still recover your nice deterministic representation in terms of y is a function of two variables. That's perfectly innocent in many situations, but I think it has done a lot of damage when it comes to interpreting counterfactuals. And so I think it's much better to just represent it, strictly speaking, as a probability, because this other variable epsilon doesn't really exist. You've just made it up for mathematical purposes. Now, the crucial point here is that all these three cases are very different and they require different solutions. And I'll make that a bit concrete by walking through the two cases that aren't problematic, or at least the two cases that are either well understood or we can understand them quite easily. Stochasticity being the one which requires some novel ideas. So here, actually, the intervention itself is not ambiguous at all. The meaning of do x equals x is perfectly clear. There's only one value of x, and it's always the same. The difference in the effect is purely due to stochasticity. So it's really wrong to speak of ambiguous interventions, even though it looks like it. And this kind of situation occurs quite standardly in the potential outcomes framework. Strictly speaking, for Pearl, this is impossible because all of his work is predicated on the idea that there is no true stochasticity. Even though there's many methods of his which could be used as well for stochastic cases, strictly speaking, that's a misusage. And therefore, it doesn't even fit in the abstraction case, because for abstractions, note that we had both at the low level and the high level structural causal models. Structural causal models are completely deterministic models. Whereas here we have something which is intrinsically non-deterministic, so it couldn't even be represented using abstractions. Now, if you're just dealing with layer 2 queries, like the average treatment effect, there really is no problem as such. Stochasticity doesn't really require too much changes in methods. And I'm just saying this without too much expertise, but I know that this is a situation that has been well studied. The moment you start thinking about counterfactuals, then things do get tricky, because Pearl is, as far as I know, the only one who's developed a clear semantics of counterfactuals. And for him, it doesn't apply to stochasticity. I do know that there's some work on the individual treatment effect, which does try to take into account stochasticity, and I should look into that more closely, because the only way I think they can make it work is by implicitly assuming some kind of semantics that does something similar to perhaps my semantics, but it's certainly not been made explicit what's going on there. Long story short, we need something novel for counterfactual side, and that's something that I think I've offered with generalizing causal models and non-deterministic causal models, and by suggesting a particular semantics for counterfactuals that would allow you to make sense of all this. So at least conceptually, I don't think this is that much of a problem. The case that is more tricky is marginalization. And to properly introduce that, I'll have to say something about the different kinds of abstraction. So I won't go through all this slide, but the main point is you can define abstractions with more and more stringent requirements, starting with the least stringent, which is exact transformation, which is a notion that predated our work, which captures many more situations than each situation that is described underneath. So going from exact transformation to uniform transformation means making it more demanding. Abstraction is even more demanding, strong abstraction further, and the most demanding of all is a constructive abstraction. And that's also the one that's most naturally intuitive. What happens is you have a whole bunch of variables at the low level, which you're going to cluster together, so that x1, x2, x3, they're all now represented by one variable x, and y1, y2, y3, they're also represented by one variable at the high level. So you're nicely partitioning all the low-level variables into clusters and representing each cluster as a single variable. Now, in our definition, we've demanded on top of that this is a strong abstraction. What that means is that, remember how I told you that the mapping for omega is somehow induced by looking at the behavior of tau? And therefore, you can say whether or not omega is defined for a particular intervention by looking at the behavior of tau. So a strong abstraction demands that you take your set of allowed interventions such that it's maximal. In other words, for any low-level intervention for which you can define omega, so it's sensible to move to the high level, you should include it. Because otherwise, the idea was something like, otherwise you're cheating a bit by saying this is an abstraction. That's because you haven't included all the details that could be included into your representation. And so it's not a perfect abstraction. Now, why does this matter? Because if we think back on our criterion for ambiguity, we get this following surprising behavior. We have that, recall in a simple example, we had x and z is being marginalized away. Think about intervention on both x and on z. We can perfectly make sense of that at the high level because z is marginalized away. So whatever the value of z is, we forget about it. And so any intervention on both x and on z is going to be mapped to an intervention just on x. Now, that means that if z made a difference, which it usually will because it's a parent of y, holding fixed x but considering two different values of z will be mapped to the same high-level intervention, yet will have different effects. And this is exactly what we required for ambiguity. Now, this is you might say, an unfortunate consequence of the definition of a constructive abstraction. It does matter, though, because this confusion is also what led me, and I think others as well, to not realize that marginalization and abstraction really are two very different ideas. And the history of this is that I discovered this mistake by reviewing a paper of Geiger and al. That took over this definition, and I pointed out, wait a minute, something's not working here. And I think there's two ways of going about it. You could just say, okay, this demands that constructive abstractions are also strong abstractions. We're going to weaken that. That's one way to go. That's perfectly sensible as a technical solution, but I think conceptually speaking, it's better to just say, look, marginalization is something very different. Let's just keep it separate. And that's how I'm going to explain why marginalization is not really a case of ambiguous abstraction. The most natural thing to do if you're moving from the low level to the high level is simply ignore interventions that include both X and Z. And so the intervention on X itself is not ambiguous. The ambiguity was simply by having this weird connection with these interventions that included Z, but the intervention on X itself should always mean the same thing. So there's no proper ambiguity, I'd say. In fact, what's going on here is we had a variable at the low level, which doesn't appear at the high level. So in other words, there's a latent variable. That is basically the standard setting of causal inference. That's what all these techniques are about. And you have to start thinking about what could be the relation between this latent variable and all the other ones. Is it a mediator, a confounder? Is it exogenous? Is it going to be stable across different settings? These are all the classical problems that causal inference is already dealing with. So this is not as such a new problem. It's also certainly not the problem of ambiguous interventions. Now, this brings me to what I say the problematic case, and I don't think it's too complicated to understand. Here, really, there is proper ambiguity. We have a low-level variable which is being coarsened, and so if we had say at the high level, for example, the high-level variable x is 1, well, we know this corresponds to 40 different possibilities at the low level. It could be the low variable could be 1 or 2 or 3 or 40. All these 40 possibilities are all consistent with this high-level intervention, and so there is true ambiguity in the most natural sense. And this is the situation that I think we should try to deal with, because it's also the situation that occurred in all the examples I gave in the beginning, right? Total cholesterol, exercise, etc. Now, what are the potential solutions? You could say, well, we're going to study this setting, but only in very specific cases, and try to be clever somehow about still being able to infer effects in this particular situation. And this is something that has happened recently, I'd say, in the literature, and one bit less recent paper. So it's definitely a good pathway to follow, but I do think it's still restricted. Whereas the fourth solution is do this in the general setting. And that's what I think I'd aspire to, have a general situation, a general description of ambiguity. The second potential solution is, I'd say, kind of the natural implicit viewpoint of abstraction people and also of Perl, as I'll show you later. Pretend that really it's just the same as marginalization. And so we can just use approximate abstraction or something similar, but we don't need to reinvent the wheel. It's just the same kind of thing than marginalization. And I'm going to show that that's really not the case. And then the third option is we're going to pretend it's the same as stochasticity, which of course we know it's not the case, but you could still do it as an approximation and then use the semantics of nondeterministic causal models. I'll go through these solutions, the first three at least, now, and I'll be, well, as I said, the fourth solution doesn't exist yet, so I'm not going to say anything more about that other than I think we should work on it. The first solution, I'll just say there's some papers on it, and I'll spend most of my time on the second potential solution. So there's a paper by Van der Wiel and Hernan from 2013, so this is in this kind of field already quite old, and yet it does discuss this issue, and it dates or it includes many of the ideas that eventually made it into the abstraction framework. So I think this is really a precursor to abstraction that I wasn't aware of until recently. The issue with that paper, I'd say, is that it's still restricting itself to a particular setting. And it's also very much formulated in the potential outcome landscape. So it wasn't that easy for me to translate everything that's going on there to the abstraction framework that's more coming from a structural causal models perspective. But disclaimer, I certainly did not study that paper to the full extent that I can make a conclusive judgment on it. A more recent paper, which I only discovered a few days ago, which actually by a colleague of mine, because she's also at UCL, Yuchen Zhu, is working within the Perlian case of structural causal models, and it's doing things which along very similar lines as what I'm going to be discussing, namely specifying exactly what form the ambiguity could take, and in each of those cases, say what we can or cannot do. It's just that as far as I can tell, the cases that are being discussed are still quite simple. And so it's not general enough to my flavor. But again, this is not in any way a conclusive verdict because I haven't done the proper work to do so, to form such a verdict. Then the last paper by Kevin Xia and Brian Boym is a much more ambitious project, I'd say, because they do try to do something general in a way, but there's lots of assumptions you have to make in terms of, not assumptions in terms of what is meaningful, what is sensible to do. And I think some of those are rather ad hoc, but again, that's a very easy claim to make without giving you the details. So I'll just leave it at, I don't think this is the end of the story, and I think there's more work to be done. But that's the work that's already out there. Now, the second possible solution would be, we're just going to pretend it's marginalization all over again. And why am I relating this to Perl? Because it brings about something fundamental about how Perl thinks of abstraction. So the Markov condition plays a crucial role in causal modeling, and Perl justifies it by saying, we start with the deterministic level. If you assume the world is fundamentally deterministic, well, then everything is just constructed in terms of equations. And if you have equations, then the Markov condition is trivial because it's just functions. So there's no problem there. We want to still have the Markov condition, even if we go up to aggregating. So what he says, these are quotes, by the way, I should have made that clear. As we move up to the macroscopic abstractions by aggregating variables. So that's exactly the kind of issue I've been talking about, right? Aggregating or coarsening is another form of aggregating, so clustering, and introducing probabilities to summarize omitted variables. That's marginalization. And he's including both of these as if they're one of a kind. Then we need to decide at what stage abstraction has gone too far, and where useful properties of causation are lost. And then essentially the idea is we want to preserve the Markov condition. So if we arrive at some abstract level and we don't have the Markov condition anymore, then we call such a model incomplete. How do we deal with such models? And this is the last paragraph. Once we acknowledge the existence of latent variables and represent their existence explicitly as nodes in a graph, the Markov property is restored. In other words, whenever you have a high-level model where there's no Markov property, you just assume that there must be some latent variable which fixes it. And you have these bidirected edges, which are usually graphically representations of that, but that's the basic idea. And that's exactly what you would do also if there was marginalization, right? You know that there's a latent variable somewhere. Now, let's walk this through a bit more in detail. So assume for simplicity that we already are sure that this new variable, which is supposedly the marginalized one, although it's not, right? We're talking about a proper abstraction. It can only be an exogenous parent of y. So we've already ruled out that it being a mediator or a confounder. How would then we apply Perl's suggestion? At the high level, we will have a function for y such that it's a function of xh, the high-level binary variable, and u for some exogenous variable u. And we have to just make sure that the distribution of u fits the distribution that we've observed experimentally and observationally for our ambiguous variable xh and the relation on y. And in particular, in this situation, the observational and interventional are going to be the same because there's no confounding going on. And so what we've done is we know that the ground truth is on the left here. There's a low-level variable, and that's the only parent of y. And we're representing this at the high level with three variables where u is some exogenous variable. Now, there's many ways of criticizing this picture. One of them is focusing on this exogenous variable and trying to understand what it means. I'm not going to go into that for now. I'll just take a simpler perspective. We know that in reality, y is determined by the low-level exogenous variable, and there must be some distribution over this low-level endogenous variable xl, right? So determined by xl, and there's some distribution. So if we use that knowledge, we get the following equalities. The probability for any particular value of y, conditioned on the high-level x being 0, is simply going to be the probability that the low-level variable xl is going to take on the value y, because the equation is simply identity, right? So y is always identical to xl, conditioned on the statement that we know xl, low-level x, belongs to value between 1 and 40, because that's exactly what xh equals 0 means. If we look at the interventional case, the same holds, except that now we're conditioning on a disjunctive intervention. In other words, we have the value of xl given that the intervention on xl is either 1, or the intervention on xl is either 2 or 3, etc., until 40. And since we just saw that the interventional and observational are identical, right, because there's no confounding, we get now that this observational statement about xl, which is entirely unproblematic, right? There exists some distribution, so we can just simply compute what that is. It's just a conditional probability, is somehow identical to this distribution that is conditional on a disjunctive intervention. Now, that's strange because the former is purely observational, the left one. The one on the right is not. And in fact, if you were to have, so the observational one is also going to depend on the latent parents of XL. So imagine we add further parents of XL, then of course, the left one distribution is going to change. We're going to get more information. The right one, it's an intervention, so that shouldn't matter. This is going to create problems at the high level, which I didn't go through in detail. At the high level, this is going to create problems because if you were to add parents of XL to the high level, all of a sudden, Y would start depending on those parents. So you'd violate the Markov condition in a very strange way. So this solution is conceptually very confusing. Also, it's not at all clear what such a disjunctive intervention amounts to. And I can just state that and hope that you agree with me, but I can also look at Pearl's work for defense of this view, because he has an entire paper on this. So he discusses disjunctive interventions, and he makes the point that it's not really clear what it means, but if we have to go with giving it the meaning, this is the best he can do. And in this situation, there's 3 variables, and x can take on 3 values, z can take on 2 values. It doesn't matter too much. The main thing is that z is a parent of x. And if we're reasoning about the intervention where x can be either x2 or x3, we have to interpret it as follows. An agent instructed to perform that action first observes the value of z, then chooses either of these actions, right? So either of these specific interventions with the probability ratio, that is the observational probability of these 2 actions, conditioned on the parent z. Now, this is sensible if you're talking about actions, meaning if you're speaking about interventional level, because then these probabilities, are probably going to be fine. Note the title here of this paper is Physical and Metaphysical Counterfactuals. If we try to apply this idea to counterfactuals, it falls apart. Imagine that we observe a particular value for x, a particular value for z, and we're in a Pearlian setting. So there exists some equation for x such that it's a function of z and some exogenous variable u. We don't know what it is, but there must exist some. So in this particular observation, there exists a value of u such that x1 was equal to this function of z1 and u, right? So the value of x1 was completely determined by z1 and this value of u, which we don't know what it is, but there exists some. If we now think about a counterfactual, so conditional on this observation, what if x were different? To compute what he's saying here, right? We want to think about the disjunctive intervention on x, and we want to look at the probability ratio that is applying here. Then we get that we have to condition on both z and u, and the probabilities are 0. Because we already know deterministically, for this value of z, this value of u, x has to be x1. So it doesn't even make sense. So this is just to give you a sense of how problematic thinking about disjunctive interventions is, and therefore it's not at all a way of escaping out of the problem of ambiguous abstraction. And I don't think we should consider it a form of marginalization at all. Now, let me just briefly say something about the third solution, namely, how about we just think of it as if it is stochastic. Even though we know it's not, we're just going to go with it and see if we can make sense of that. What that means is we take this probability of y given the high-level variable x as irreducible. We're not going to consider this in terms of some low-level model. The probability is just there. Note that this again means that this is not within the scope of causal abstractions, because there all probabilities are entirely reducible to probabilities over exogenous variables. You can pull out the probabilities. This is not the case here. So we need to invoke non-deterministic counterfactuals. For example, my own papers that I already mentioned earlier, but of course, people are free to use other semantics if they think those are better motivated. And at least on the positive side, this is conceptually clearly defined, right? We can make sense of what these probabilities mean. Namely, these are just stochastic relations. The downside is that it's not true. So we're losing accuracy because we're representing something in a manner that is not truthful. And let me just briefly say where this loss comes from. What exactly are we misrepresenting here? Well, there's pretty strong assumptions that have to be made for this stochastic representation and the ambiguous representation to somehow line up and give you the same result. Namely, under a stochastic view, this ambiguity is going to be identical whether you're looking at observations or interventions, because the ambiguity is not in any way due to how the intervention variable, let's say x, how it was caused. That's not what the ambiguity is. So whether you're looking at intervention or observation, it doesn't matter. It's always going to be the same kind of ambiguity. Also, ambiguity of x relative to one effect y is supposed to be or assumed to be independent of the ambiguity of x relative to some other variable z. Because if there's stochasticity here, then there's no reason whatsoever why these stochastic relations should somehow be connected. They could be, of course, in general, but the default setting would be we consider them separately. Whereas if you think of ambiguity of x in terms of multiple values, well, then y and z are going to all of a sudden be correlated because learning a value of y can tell you something about the particular value that x took that gives you information about z. So even conditioned on x, y and z are not going to be independent, violating the Markov condition. So that's something which wouldn't be true in the stochastic setting, and therefore, again, we have to assume that somehow this doesn't occur. And the more complicated point, I've only spoken about one intervention variable, x. What if you're thinking about multiple parents and there's ambiguity regarding the relation between those parents and y? The stochastic framework that I'm proposing somehow assumes that ambiguity is entangled with all the parents together. They're all contributing in the same way to one source of ambiguity. And again, if you were to work it out in detail with this idea of there's a low level, that need not be the case. So that's a special case. And whenever these three cases are not representative of what's really going on, you're losing the accuracy of your representation. But I understand that this was all pretty vague. The good thing is that this was the last slide, so I'm going to stop right now and leave some room for questions if you have any. Thank you.
Yep. Thank you, Xander. Let's thank our speaker. Thank you. That was very interesting. Do you have any questions online? I think we have already one from Kurt. It's in the chat. We can go with that first. So I know if Kurt want to, Kurt, do you want to ask that also verbally right now, or?
Yeah, I guess I can. So basically, the way I understood a statement earlier in the talk is that when you do something like coarse graining, so you start with a variable like I don't know, blood pressure or something, and that ranges from 0 to 200 on some scale. And then you coarse grain it, so now you break it into low blood pressure and high blood pressure, and that's your new variable. I understood that you said that when you coarse grain like this, you induce some kind of stochasticity. So now if you had some mapping that would take you from one coarse grain variable to another, it might be deterministic before, but now because you only have low and high, you have uncertainty about where you are. So now there is like uncertainty in that mapping. So now there's a random variable involved. But when I thought about this, I kind of realized it was not so obvious to me, because in this assumption, you're still assuming somehow that you have probability on like where you are in that spectrum. So for this unit like blood pressure, you're somewhere on that spectrum between 0 and 200. So there has to be some probability on where you are. for that to induce a probability after coarse graining. So when you look at like these abstractions, what do you mean that you can take a deterministic model and abstract it to a stochastic one, I guess after marginalization? It was somewhere on the background on abstractions.
Sorry, so where?
Yeah, this like this thing where you start with y equals g of x, and then it turns into y equals f of x and z. Like, how can z appear if there wasn't randomness already there?
No, sorry, z is the one that's being marginalized, right? So z is disappearing. So we're starting with something. So that's the thing. Stochasticity isn't really involved at all. It's only in the last solution that I proposed that we could pretend it's stochastic, but there's nothing stochastic going on whatsoever. It's all deterministic. It's just that we don't know enough. And so if we're now saying, so this case, it's in this case we don't know enough because there's a variable we don't know, z. And that's why I'm saying this is a standard case in causal inference. Like there's a missing variable, so obviously we're not going to be able to predict everything that's going on. But the case that I think is more interesting, the coarse grading, is not this, right? The coarse grading precisely means there is no z. It's just that we're going from xl to xh. And how do we represent that somehow? So sure, probabilities are going to arise at the high level. How do we think about those probabilities? And how do we fill in the picture if you want to, for example, if you want to move towards a structural causal model, what would that look like? And I'm saying that challenge hasn't been met. And in fact, I don't think there's any good way of arriving at a structural causal model, because then you're going to make something deterministic. Yeah, that's, I won't go into that more deeper because that's another topic. But to be clear, this is not a situation that I think is problematic. The situation that's problematic is the second one.
Okay. All right. Thank you.
Matthew, yes, I think you have a question.
Yeah, I'm gonna ask a very practical question, if that's okay. So, as you saw, we spoke last week about the Cherry project. So I'm a very practical person. I'm dealing probably a lot with ambiguous interventions. So let's say in the example of cardiovascular prevention, all I know about an individual is that they're a smoker, an ex-smoker, or a non-smoker. And let's say for smokers, I'm interested in, what would be the effect for this individual of a smoking cessation intervention of some kind. So I guess so I think what I'm therefore doing is abstraction, because I'm coarsening. So, so I'm saying this is a smoker rather than this person smokes however many cigarettes a day or has this many pack years cumulatively over their history. So I guess how much trouble am I getting myself into by taking a pragmatic approach of, well, on average, so I suppose I'm doing a sort of stochasticity style approach. On average, for stopping smoking has a risk reduction of 25%. So let's apply that to this individual. I mean, I guess, how bad is that? Or is that reasonable as a pragmatic type approach given these issues?
I think part of the problem is that I don't have a clear answer as to saying how bad it is, because we don't have a proper way yet of truly representing it. But it's the situation. So I wanted to use an example that you gave in your talk last week, because it was a very clean example of ambiguous intervention. And it is completely permeating causal inference. And the standard answer is, well, we have to try to specify our intervention as much as we can. And it's going to be based on our expert background knowledge as to whether or not it's specific enough. So perhaps some expert might say, smoking cessation, that's not clear enough. You should distinguish between, do they start vaping or do they start using nicotine patches? Or because if you really believe somehow that these are going to be different, you should have that variable. But at some point you have to say, this is probably good enough. And you have to go with it. And you'll never find out, well, you'll never be certain whether that was good enough, because you're not going to go further down. And what I'm trying to get at is, it would be good if we had a clean way of characterizing at least what loss is involved in making that assumption. For example, clarifying what would be the worst case if the situation were actually like that, were actually that these different versions had gigantic differences. And in the general setting, I don't think that's around. Although I would imagine that the paper by Van der Wiele is already getting pretty close to perhaps what you would like to use, because it's very much within the standard potential outcome setting where you have one treatment variable, and he distinguishes between two different kinds of ambiguity. It could be that you first specify the version and then the treatment, or you could have first the treatment and then the version, and these require different approaches, but it is very much motivated by exactly these kinds of situations. So the short answer I should have given is maybe look at that paper.
Thank you.
Out of time, I can ask a quick question.
We have, oh, well, it's not up to me. So Anna here next to me has a question, but he's not, we're sure there's time.
No, if there is one more question, sure, we can, I think, do that.
Okay.
So, you know that you focused on the stochastic approach, but you also mentioned other cases where there is a ambiguity in the interventions in the abstraction. And those are, so they remind me very much of the approach that has been known for a long time in verification, actually, where models are abstracted because of their size, right? And then you look for counterexamples or results on the abstracted models, and then sometimes they're ambiguous, or they get spurious counterexamples, which are not really counterexamples, etc. Except for exactly the same reason. So it's called the Seeger framework. So perhaps what you're suggesting can give rise to appropriate refinement, or what you're suggesting, what you overviewed here, to iterative refinement of the abstraction, to bring it exactly to the level when it's still abstract, but there are no ambiguous interventions.
Okay, that's certainly a connection I'm not aware of. I would wonder though, presumably because it's about computer programs, even the coarse-grained version is still going to be very entirely deterministic, right?
So it is deterministic, but it might result in what they call spurious counterexamples. It might result in executions that don't correspond to anything in the real program. And when we translate it to causal models, right, it might result in some, something that is actually doesn't occur in practice. It occurred only because of your wrong abstraction, or this too coarse abstraction.
Yeah, I would imagine that fits within the same conceptual scheme, at least, as the marginalization solution, so that we just pretend it's marginalization. So we're going to have to add other details that then determine the output.
Exactly that, yeah.
And so the Pearlian perspective would be one choice. We have these response variables, but you could imagine that presumably that's not what's going to happen in this context. So there's going to be other ways of somehow filling in the non-determinism that arrived.
So it's abstraction refinement. So the framework there is called, for example, guided abstraction refinement. But here it can be ambiguity guided abstraction refinement, right? So every time you have an ambiguity, you add a little bit from the concrete model, or you refine the abstraction a bit.
Okay, so it's kind of an iterative thing where you
iterative.
try to abstract. If it doesn't work, you say, okay, that seems a more operational approach to saying, okay, assume we have the ground truth low level model. We don't want to use it because it's a lot of work, but let's try to figure out if we remove this, do we get ambiguity? Okay, then we add this. That's certainly a perspective that could also apply here to figure out this work on looking for optimal abstractions. Currently, it's always seen in terms of when do we simply stop having an abstraction, whereas it could also be, well, what if we're willing to accept some ambiguity in some places of the high-level model? The search now becomes a bit different. It's then simply,
So just the direction is you don't start with a complete one, you start with a very abstract one, and you refine it based on this bad ambiguous examples that you're getting from running it.
Yeah.
Until you decide that you're fine, right? You're not getting bad examples anymore.
Yeah, I would imagine that if that's a well develop fields,
yes.
ideas from that could translate to the similar idea of abstraction.
That's what I'm
Um,
thinking. Yeah, it is a very well developed tool.
Yeah. Okay, that's something to look into.
Yeah, absolutely.
Nice. And I was just wanted to add because I had a quick question and that discussion like made me think a bit more. So if you have that setting of low level regime, I wonder if unless there are already works that you aware of that for you to somehow identify the breaking point. So maybe we can find the sweet spot of where maybe we can abstract a little bit and we're still fine in terms of causal effect estimation, but then there is a breaking point of if we go beyond certain threshold, things fall apart. And maybe just identifying that breaking point will be also maybe useful.
Yeah, and in general, it's always going to be very much relative to what you care about, right? Because you can get rid of all ambiguity by just abstracting the effect variable as well. Right, so there's always going to be a trade-off of, let's say you have effect variable, and ideally you'd like to care about it as much as possible, but you would also like to abstract the treatment variable. Okay, then there's a trade-off. Like this much abstraction of the treatment variable introduces this much ambiguity. So to get rid of that, you could simply say, I'm going to abstract as well the effect variable, and yeah, it adds another parameter to the space, the search space of finding an optimal abstraction. Yeah.
Okay, nice. Thank you. Okay, I think this might be a good time to close our session. Thank you again, Xander, for your talk. Thank you very much.
You're very much welcome.
Okay, so